Good morning. My name is Barbara Imhoff and I'm a design researcher and space architect. I co-manage Liquifer Systems Group, a design-focused company comprising space systems engineers, scientists, designers and architects. We work in research and development projects for space exploration and also pursue the topics of biomimetics and integrating biology into architecture towards a living architecture. The overarching theme of this conference is living machines, and in the course of my presentation I will also address the topic of this workshop, Growing Structures, Bioinspired Innovation Insights for Architecture and Robotics. Living machines. When we think of living machines, we might think of the following movie.
29-year-old female, diagnosed as acute schizoaffective disorder. She believes that a machine called a Terminator was sent back through time to kill her.
This, of course, is a snippet from the Terminator 2 trailer, and this is probably one of the icons of a living, intelligent machine. The scenario is set far in the future. New spaceships are a little bit like this, intelligent and living machines. However, in space exploration today, we see that a space station is solely a machine and with hardly any intelligence as we imagine it. But we are gearing up towards creating this new environment. Current plans for the new moon orbiting station called Gateway are underway, and it should be implemented in the next couple of years. It is a new project by the International Space Station partners, and we as Liquifer are contracted to design the interior for the International Living Module, which only foresees robotic automation intending the station remotely when not inhabited. Gateway is meant for a crew of 4 to live there up to 1 month. When inhabited, the humans require a specific environment to live in, regarding temperature, pressure and air. What you see here is pressure vessels in an environment which is a vacuum and which is very cold and very hot at the same time. So we need a life support systems, and together with these pressure vessels, this creates this highly technologized environments where humans can thrive in. Like the International Space Station, Gateway is a zero-G environment, and that is an environment where all the X, Y and Z axes are perceived in the same way. So we can perceive the space much larger than it actually is or would appear to us when we would be in a 1G environment on Earth. To give you a better feeling of how humans move within a 0G environment, here is the next video snippet. It is the ISS commander Sunita Williams floating in the International Space Station.
I'm coming down. Woo! Then you can come right back up again, like Superman. Woo!
In the future, however, we will build space stations or planetary bases which are being built by autonomous robots and which will be bio-inspired and integrate biological systems, as we can see in the current developments, which I will show later. The International Habitation Module for Gateway is rather small. It has to comprise a lot of different functions, living and working equally, to be able to sustain and to provide a good environment for these 4 humans, which are supposed to live there for 1 month. you see that it's also a quite complex environment. We need a lot of storage space, that is space where food and spare parts are being stored. We also need a sort of small kitchen. It's a galley with a food warmer and a water dispenser, a trash compactor. You will also see that there is a tabletop integrated. It is deployable and transformable, and where 4 people can sit and have dinner together. Exercise devices are vital because in zero gravity we experience bone loss and muscle loss. The crew quarters are deployable, important factor. They provide a private atmosphere, private space, and also are larger when we need them in the night and smaller during the day. The toilet is on the top, so it cannot be seen easily from the crew quarters, but people know where to find it. There's a freezer, there's science equipment, there's also, of course, a general control station for gateway, and there's a large volume which is part of the systems and the life support system. So when we float into that space, we see that it appears to us quite small. However, because it's 0G, we can really make use of all 3 dimensions. You see here the glove box, you see the control station again, and you'll also see the table, which is being used for common dinners and for gatherings of the crew. In the future, when we look at life support systems, we will imagine them to be different. One example is the water walls architecture. It was conceived and developed by Michael Flynn from NASA Ames Research Center in collaboration with Mark Cohen and Renee Matosian, 2 architects and others. It is interesting because in the water walls architecture, which is a massive, redundant and highly reliable life support system for long duration exploration missions, living material is integrated, algae and bacteria, to purify the air and consume the nitrates. So the water walls architecture processes wastewater, air, controls the air, and the climate, and produces power. The whole system comprises of bags with fluids which can be exchanged when malfunctioning, and at the same time the water walls can protect spaceships from radiation when traveling outside of the Van Allen belts. So the water walls are really a step towards a living system and a living architecture. A project under this name, Living Architecture, was developed by a large consortium under the lead of the University of Newcastle and Rachel Armstrong, and we as Liquifa were partners for the architecture. The premise in this project, Living Architecture, was to create a 3-in-1 bioreactor which produces energy, cleans grey water, and retrieves valuable resources such as phosphate through synthetic microbial consortia. So this 3-in-1 bioreactor can be imagined to become part of the water wall system, although it was not originally conceived for space, but it yields the concept of recycling and reusing resources, and the house or the spaceship being more autonomous with regards to waste treatment. In this small animation, we see the conceptual approach of combining various bioreactors, and besides the microbial fuel cells, the photobioreactors, and also the synthetic biological reactors with synthetic microbia, together they present this 3-in-1 large bioreactor. So when we imagine a living life support system, thus staying with sustainable approaches for building a lunar base, this also implies living off the land. So what resources do we have available on the moon? We have the sun in abundance, and we have the sand, the lunar sand. In Project Regolith, which was an EU-financed project under the lead of the DLR in Cologne, Liquefied developed, in collaboration with other partners, a technology which can create interlocking building elements, as you see in the picture here, to build bases which can be inhabited by humans but could also provide shelters for robots on the moon, and which use very simple technology of solar sintering, 3D printing technology. And this technology is really about concentrating a solar array and melting or gluing layers of sand in an additive layer manufacturing process together, so that interlocking building elements for various applications can be built and can then put one on top of each other, become habitats for pressurized volumes or shelters for robots or other machines to protect from the lunar abrasive dust, and form terrains for a lunar telescope or for a launch pad apron. So here you see the concept. So regolith, lunar regolith, can provide humans, or can protect humans from radiation and micrometeorites. It is a 2 to 3 meters thick envelope, protective envelope, and within that we create the pressure vessel we need through an inflatable skin, which can then inside provide the environment humans need to live in. For Project Regolith, to test and develop the technology, we created different printing campaigns. One was in vacuum, so on the left-hand side you see the setup with the vacuum chamber. Inside of the vacuum chamber there was a 3D printer, solar sintering printer. You see the prototype on the right-hand side. And on the big picture on the left-hand side you also see how the xenon lights really beamed light onto the mirror, which then concentrated it into the vacuum chamber. Another test we made was with an XYZ table. You see a table moving. On the table there are layers of lunar regolith simulant being deposited, and then through a solar beam projected through onto the mirror and onto the table, interlocking building elements were sintered in an additive layer manufacturing process. To scale up that experiment, we also created a large printer which can be envisioned to, with wheels, to become a mobile printer, a robot printer, and it has a moving Fresnel lens which moves according to the sun, and a larger building volume which can create big interlocking building elements which can then be used for the various applications such as habitat envelopes. This is a prototype here of a solar-centered element. It is already quite dense, quite stiff and hard. It can only take pressure compression forces, no tensile forces. So the geometry of the habitats have to be such that it is a more dome shape habitats to withstand the forces they need to withstand. You also see that the technology needs to be further development to avoid the bending on the side. As a geometry, we used rhombic dodecahedron space filler geometry. You see here, you also can see that it has obtuse angles because with the sintering technology, no sharp angles can be printed. And this geometry can be built up in different shapes and sizes so that it actually can become larger elements, or larger elements can be solar centered to form the protective envelope against micrometeorites and radiation for the lunar habitat. And inside you also see there are inflatable shells, hulls, which need to be carried from Earth. These or the shells or these inflatables need to be transported by rockets. So wood packing is quite of the essence. So in a former project we looked at different kind of biological role models, how beetle wings fold or how cactus grows or a mussel shell grows, and what the advantages and disadvantages are when being applied to, for example, for a lunar habitat, inflatable habitat geometry. And this is the example for a mussel shell. They all have different pros and cons and need to be investigated when the application is further developed or the selected geometry is being chosen. A more recent development is towards self-growing buildings. This is a picture you see. It actually stems from the project Growing as Building. It was an artistic research project with a couple of partners, including Julian Vincent, Petra Gruber and Thomas Speck. It was run at the University of Applied Arts, and it looked at the self-growing house. So what kind of, when we look at nature and biology, what kind of paradigms or role models can we find to apply to a house, to a self-growing house? One stream of investigation was mycelium, looking at mycelium and how we can grow structures from mycelium. So we specifically looked at mycelium grown on cotton. You see on the left-hand side some prototypes, and the interesting part is that actually the mycelium hardens the soft membrane structures and allows then the membrane, which is originally only has tensile, can take tensile structures, to also take compression forces, and then in this top left example can be turned 180 degrees to become an arch. So there's a lot of potential, and this is not only seen by the by us, but also by Ames Research Center under the lead of Lynn Rothschild. It is about microarchitecture off-planet, growing surface structures at destination, and they have been looking at Mars habitats. The other interesting aspect is that at the same time, extreme Antarctic fungi survives a Martian habitat, a Martian environment, as well as a space environment. So there is evidence that specific fungi and mycelium can be used in a Martian environment. The later research was conducted in a collaboration by the European Space Agency and the German Aerospace Center in Berlin. So with this short presentation and snapshot of recent developments in space architecture for bio-inspired and biomimetic space architecture, we can see that there's a new path growing. in that direction. And I'd like to close with a quote by Thomas Speck, who also has collaborated, as I mentioned earlier, with us on the project Growing as Building. He says, "Biological solutions are fantastic role models for a new bio-inspired architecture in which living and non-living matter may eventually be combined." Thank you.